Yo, Ryan. Check this out. Check this out.
Whoa! It's a treasure map! Dude, that's crazy!
Yeah, I know, right?
Yo, what kind of treasure could be here?
I know, right? Just look at it. It's a math problem.
That's awesome. Yo, let's solve these problems together and find the treasure. Wait, where'd he go? Well, I guess I'll find the treasures then.
So we need to determine the domain of the function given by y equals e over x squared minus pi squared. It's important to note that e and pi squared are constants. X squared will give you real values for all real x, and adding two real values will end up results in a real value as well. However, dividing two real values will give you a real value unless the denominator is 0. And since the function is e over x squared minus pi squared, in all situations where x squared minus pi squared equals 0, the function will not have a real solution. So we need to find all solutions for x when x squared minus pi squared equals 0. You can use difference of squares to determine that x squared minus pi squared equals x minus pi times x plus pi. So x equals negative pi and pi. Therefore, x cannot equal negative pi or pi to result in a real answer to the function y equals e over x squared minus pi squared. Therefore, the domain of the function given by y equals e over x squared minus pi squared is x is less than negative pi is less than x, which is less than pi, or x is greater than pi.
Okay, I found the domain. Now I need to find the range.
Now we need to determine the range of the function given by y equals e over x squared minus pi squared. In order to do this, we need to do the first derivative test to find where the graph changes from increasing to decreasing or vice versa. This is done by finding the critical points and assessing whether or not the derivative is positive or negative before or after the point. Then we need to check whether or not the point is a minimum or maximum. This is because if it's a minimum or maximum, we know that in the segment of the domain, the range is limited to below or above the maximum. So if we do the first derivative test on y equals e over x squared minus pi squared, we get that y prime equals negative 2 ex x squared minus pi squared to the negative 2. From this, we can determine that y has a stationary point at x equals 0, and other critical points at x equals negative pi and x equals pi. Since x is squared, we know that x squared minus pi squared to the negative 2 will be positive for all real values. For x is less than negative pi, e times 2x times negative 1 will be positive. So that means the slope will be positive when x is less than negative pi. When x is greater than negative pi but less than 0, e times 2x times negative 1 will be positive. So the slope will be positive when x is greater than negative pi and greater than 0. When x is greater than 0 but less than pi, e times 2x times negative 1 will be negative. So the slope will be negative. With x is greater than pi, e times 2x times negative 1 will be negative. So the slope will be negative when x is greater than pi. Because it goes from increasing to decreasing at x equals 0, x is maximum at x equals 0. Thus, between negative pi and pi, the range of the function will be from negative infinity to f of 0, or negative infinity to negative e over pi squared. Because y approaches 0 at x equals negative infinity and infinity, we can tell if it's above or below 0 by testing the values x is less than negative pi and x is greater than pi. For both, it turns out that x squared is greater than pi squared. So x squared minus pi squared is greater than 0. We also know that e will always be positive, so the function's range is bounded in 0 to infinity. In the domain, x is less than negative pi and x is greater than pi. Now we can combine them to find that the range of the function of e over x squared minus pi squared is from negative infinity to negative e over pi squared and 0 to infinity.
Alright, nice. I found the range. Now I know where the treasure is. But I still need to figure out this path of how to get to the treasure.
We need to determine the intersection of the ranges of the functions given by y equals sine of x and y equals cosine of x. Since both sine and cosine are functions that are periodic with a period of 2 pi, we can look at the domain from negative pi to pi to find where their ranges intersect. For clarity, we're going to call sine of x f1 of x and cosine of x f2 of x. To start, let's use the limited domain and range of sine x and cosine x. The domain is negative pi to pi and the range is negative 1 to 1. When looking at sine x, because the y values increase as the x values increase in the domain negative pi over 2 to pi over 2, the minimum must be sine minus pi over 2 and the maximum must be sine pi over 2 over that interval. So when looking at sine of x, since you know the min and max of sine of x, you can plug that in to determine the min and max of sine of x. So sine of negative pi over 2 equals sine of negative 1, and sine of pi over 2 equals sine of 1. Pi over 2 is greater than 1, and we already established that the y value increases as x increases from negative pi over 2 to pi over 2. Therefore, we know that the minimum of f1 of x must equal sine of negative 1, and the maximum of f1 of x must equal sine of 1. Cosine is increasing from negative pi over 2 to 0, and decreasing from 0 to pi over 2. So it has a maximum at cosine 0, which equals 1. And since cosine pi over 2 equals 0, we know cosine of pi over 2 equals 1, and the maximum of f2 of x is 1. As cosine x is symmetrical, we only need to look at one side to find the minimum. Because cosine x is decreasing from 0 to pi over 2, as the input x gets larger, the output cosine x gets smaller. Therefore, to find the minimum of cosine of x, we have to use the maximum of cosine of x, which is cosine 0, which equals 1. Cosine of 0 equals cosine of 1. Therefore, the minimum of f2 f2 of x must equal cosine of 1. We know that sine of 1 is less than sine of pi over 2, and sine of pi over 2 equals 1. So f2 of x's max must be above f1 of x's max. So the intersecting ranges must be between the max of f1 of x, which is sine of 1, and the minimum of f2 of x, which is cosine of 1. Since 1 is greater than pi over 4, you can look at the graphs and tell that sine of 1 is greater than cosine of 1. Thus, the intersection of their ranges will be cosine 1 to sine 1.
Alright, I found the path. Now, I definitely know where the treasure is. Okay, time to get the treasure. Here it is. It's the treasure. Alright, let's dig this up. Alright. Wait, there's nothing here. What the heck? What? What the heck? What's the... No! Let me in!
This is all a trick. It's revenge. Revenge for the last time.